Hello everyone, welcome back to the Medicinal Chemistry course presented by Parasympathomimetic Academy. I am Noor Adra, a fourth year pharmacy student at LAU, and I will be presenting the first part of the chapter about drugs affecting cholinergic neurotransmission. So in this lecture, we will start with a short introduction, and then we will discuss the biosynthesis, storage, and release and fate of acetylcholine. We will talk about the different types of cholinergic receptors and the classification of cholinergic drugs. And then we will explain the structure-activity relationships of agonists and discuss exceptions to the SAR. The last section will be about indirectly acting sympathomimetics as well as acetylcholine esterase inhibitors antidote. Cholinergic drugs affect the parasympathetic nervous system. Acetylcholine is the main neurotransmitter of the parasympathetic nervous system, and once it's released from cholinergic neurons, it will bind to receptors on the effector cells, stimulating different types of response. For example, salivation, digestion. It will stimulate contraction of smooth muscles, either in the GI tract, urinary tract. Usually those responses are called rest and digest responses. Acetylcholine is biosynthesized in cholinergic neurons by the enzyme-catalyzed transfer of an acetyl group from an acetyl-CoA molecule to choline, a quaternary ammonium alcohol. Most newly biosynthesized acetylcholine is actively transported into cytosolic storage vesicles located in the presynaptic nerve endings. Release of acetylcholine from the storage vesicles is initiated by an action potential that has traveled down the axon to the presynaptic nerve membrane. This action potential leads to the opening of voltage-dependent calcium channels, affording an influx of Ca2+ and exocytotic release of acetylcholine into the synapse. Now, acetylcholine in the synapse can bind with cholinergic receptors on postsynaptic or presynaptic membranes to produce a response. Free acetylcholine that is not bound to a receptor is hydrolyzed by acetylcholine esterase in the synaptic cleft. Acetylcholine hydrolysis by acetylcholine esterase is the physiological mechanism for terminating the action of acetylcholine. Acetylcholine esterase binds to the esteratic site of acetylcholine by attacking the ester of acetylcholine through a serine hydroxyl group, or the anionic site through electrostatic attraction. Then once acetylcholine is hydrolyzed, the choline fragment is reabsorbed by the presynaptic neuron and recycled back into acetylcholine. Two types of cholinergic receptors exist, nicotinic and muscarinic receptors. In nicotinic receptors, we have the NM receptors, which stand for muscles, and the NN receptors, which stand for nerves or ganglia. Muscarinic receptors are divided into 5 subtypes. Depending on the type and location of receptors stimulated by acetylcholine or any other cholinergic agonist, relaxation or constriction might occur. For example, acetylcholine acts indirectly to dilate blood vessels through binding to muscarinic receptors on the endothelial cells of the blood vessels, causing release of nitric oxide and therefore vasodilation. On the GI tract, for example, acetylcholine binds to muscarinic receptors to increase secretions and therefore increase motility in the GI tract. Now, once you see the effect of acetylcholine on these different types of organs, one can imagine what a cholinergic antagonist might do. For example, a cholinergic antagonist will cause mydriasis and loss of accommodation in the eyes, in contrast to a muscarinic agonist, which causes meiosis. A cholinergic antagonist may cause bronchodilation, which is an anti-asthmatic effect, in contrast to muscarinic agonists that cause constriction in the bronchi of the lungs. And cholinergic antagonists may also decrease intestinal motility and can act as an antidiarrheal agent, in contrast to what we mentioned before, to acetylcholine, which increases secretions and therefore stimulates diarrhea in the GI tract. Two types of cholinergic drugs exist, and they are classified into parasympathomimetic drugs, which mimic the effect of the parasympathetic nervous system and so are called agonists, and parasympatholytics, which inhibit the effect of the parasympathetic nervous system and are called antagonists. In this lecture, I will mainly focus on the agonists. Parasympathomimetic drugs are further classified into directly and indirectly acting. Directly acting means that the drug directly interacts with the receptor, either muscarinic or nicotinic receptors. Indirectly acting acts through inhibiting acetylcholinesterase enzyme, which is responsible of the degradation of acetylcholine. This is the structure of acetylcholine. As you can see, it has an ester moiety as well as a quaternary ammonium moiety, which makes it ionized. And this ionization is one of the reasons acetylcholine is a poor therapeutic agent, since it is hardly absorbed through lipid membranes of the human cells. And moreover, one should note that acetylcholine is a non-selective cholinergic agonist, which means that it binds to both muscarinic and nicotinic receptors, which also adds on the poor therapeutic character of acetylcholine. Now we will move to the section about structure-activity relationship of the agonists, which will be derived from the prototype, which is acetylcholine, through some modifications to the structure. Only compounds possessing a positive charge on the atom in the position of a nitrogen had a good muscarinic activity, which means that a positive charge on the nitrogen atom specifically is essential for activity. Therefore, replacing the nitrogen with a phosphate group, for example, will decrease muscarinic activity. Moreover, compounds in which one or all of the three methyl groups on the nitrogen are replaced by larger alkyl groups will have a decreased agonistic activity as well. When the methyl groups are replaced by three ethyl groups, like in triethylammonium, for example, we will have an antagonistic cholinergic activity. Now, moving to the ethylene bridge, one should keep in mind the rule of the 5 atoms. This rule suggests that there should be no more than 5 atoms between the nitrogen and the terminal hydrogen atom for maximal muscarinic potency or activity. Therefore, any removal of the ethylene group, decrease or increase in the chain length, will lead to a decreased muscarinic activity. However, when it comes to branching on the ethylene bridge, an alpha-methyl branch will increase the nicotinic activity and therefore increase selectivity to the nicotinic receptors. A beta-methyl substitution will increase muscarinic activity. However, if the R group is larger than a methyl group, this will decrease activity and increase toxicity. Here we have two examples of two molecules that do have a methyl substitution on either the alpha or beta carbon. For example, methacholine or acetyl beta methylcholine chlorides will have a beta methyl substitution on the beta carbon, and this leads to more selectivity to the muscarinic receptors as we mentioned before, and this molecule is more resistant to acetylcholine esterase. Because it causes steric hindrance around the ester group of the molecule. Another example is acetyl alpha-methylcholine chloride, which does have an alpha-methyl group on the alpha carbon, increasing its nicotinic activity. Concerning the acetoxy group of a molecule, any increase of size in this group will lead to a decreased agonistic activity, with some exceptions that we will talk about in a bit. Now, esters derived from carbamic acid are referred to as carbamates, and because their carbonyl carbon is less electrophilic, the carbamates are more stable than carboxylate esters to hydrolysis. Carbachol, for example, exhibits greater stability than acetylcholine towards hydrolysis by gastric acid, acetylcholine, or any other esterase, and therefore it can be administered orally. Beta-nickel is another example, which is derived from carbachol by alpha-methyl substitution. So it is the carbamate analog of methacholine. It's also potent and selective muscarinic agonist. Now let's take a while and summarize our ideas concerning the SAR. So as we mentioned, the molecule must have a nitrogen atom capable of bearing a positive charge, preferably a quaternary ammonium salt. And for maximum potency, the size of the alkyl group substituted on the nitrogen should not exceed the size of the methyl group, otherwise we will have decreased activity. The molecule should have an oxygen atom, preferably an ester-like oxygen capable of participating in a hydrogen bond. Moreover, there should be a 2-carbon unit between the oxygen atom and the nitrogen atom for maximum activity. Now we will start with the section about exceptions to the SAR. As we go through this section, I want you to please keep in mind what we talked about regarding the SAR, and you should be able to notice the difference. The first group is choline ethyl ether, which exhibits significant muscarinic activity and is chemically stable despite it violating the SAR rules. Another group of molecules are the alkyl aminoketones, which also exhibit good agonistic activity. Our next molecule is muscarine, which is obtained from Amanita muscaria mushroom, and it is one of the oldest known cholinergic agonists, and therefore muscarinic acetylcholine receptors are named after this molecule. The next molecule is pilocarpine, which is produced from Pilocarpus jaborandi, and it is also a potent muscarinic agonist. Pilocarpine is inactivated either by hydrolysis into pilocarpic acid or through epimerization into isopilocarpine. Parasympathomimetic drugs are further classified into directly and indirectly acting. Directly acting means that the drug directly interacts with the receptor, either muscarinic or nicotinic receptors. Indirectly acting acts through inhibiting acetylcholinesterase enzyme, which is responsible of the degradation of acetylcholine. Another means of producing a cholinergic response is to interfere with the mechanism by which the action of acetylcholine is terminated. Therefore, inhibition of its rapid hydrolysis by acetylcholinesterase increases the concentration of acetylcholine in the synapse and results in a production of both muscarinic and nicotinic effects. So we are talking about the indirectly acting parasympathomimetics, which are divided further into reversible acetylcholinesterase inhibitors and irreversible acetylcholinesterase inhibitors. Now, starting with the reversible acetylcholinesterase inhibitors, and before discussing the drugs, I want you to keep in mind 2 points. First point is that aryl carbamates have a higher affinity for acetylcholinesterase than alkyl carbamates. And another point is that the rate of hydrolysis of a carbamylated acetylcholinesterase is much slower than the acetylated enzyme. So if you look at the pictures on the right, you can see the difference between a carbamylated acetylcholinesterase and an acetylated esterase. So this means that a carbamylated acetylcholinesterase is regenerated quite slowly. And this is the case with physostigmine, which is a tertiary amine alkaloid obtained from a natural source. It has a high affinity to acetylcholinesterase and it is light sensitive. Concerning the inactivation of physostigmine, it is inactivated by hydrolysis into acetylcholine and further into another inactive compound, which is rubricillin. The next two drugs are neostigmine and pyridostigmine, which are both synthetic compounds used for myasthenia gravis, and as you can see, they are both ionized. Propoxur is another reversible enzyme inhibitor, and it is used as an insecticide. Now, these three drugs can be used for Alzheimer's disease. Just note that tacrine is hepatotoxic compared to rivastigmine and donepezil, which are not hepatotoxic. Another interesting drug is edrophonium, which is used for diagnostic purposes. It is used to distinguish between myasthenia gravis and cholinergic crisis. Just a reminder that myasthenia gravis is an autoimmune disease characterized by a reduction of the functioning nicotinic receptors, while cholinergic crisis, as the name indicates, is an excessive cholinergic activity. So when you give edrophonium, which is cholinergic agonist, to a myasthenia gravis patient, symptoms should be improved, while edrophonium giving to a person suffering from cholinergic crisis will even worsen the symptoms of the patient. Moving to the last class of drugs I will be covering in this lecture, which are irreversible acetylcholinesterase inhibitors, otherwise called organophosphates. These drugs will inactivate the enzyme by phosphorylation, and a phosphorylated acetylcholinesterase enzyme is very stable to hydrolysis, which means almost irreversible inactivation of the enzyme. These are the molecules that belong to this class, and one should note that they all do have an organic phosphate that will be used to form phosphate ester with the acetylcholinesterase enzyme to inactivate it. Parathione, which has low anti-acetylcholinesterase activity, can be converted into paraoxone, which has a higher cholinergic activity. And this reaction can occur in the human body, for example. If a patient ingests parathione, his body's oxidase enzyme can catalyze this reaction, which might lead to toxicity. Malathione is activated by slow microsomal oxidation into malaoxone, which is a potent acetylcholinesterase inhibitor. Naloxone in insects is transformed through phosphatase into dimethylphosphate, which is an inactive molecule. Malathion in humans or in mammals in general is converted by carboxyesterase into malathion acid, which has a poor cholinergic activity. Antidotes for acetylcholinesterase inhibitors do exist, and they are called Oximes. They are used to regenerate the enzyme after binding to the inhibitors. The proposed mechanism for regeneration of acetylcholinesterase by Oximes or by 2-PAM in this example involves an initial step that consists of binding of the quaternary ammonium nitrogen of 2-PAM to the anionic binding site of the phosphorylated acetylcholinesterase enzyme. This places the nucleophilic oxygen of 2-PAM in close proximity to the electrophilic phosphorus atom. So nucleophilic attack of the Oxime oxygen results in breaking of the ester bond between the serine oxygen atom and the phosphorus atom. The final products of the reaction are the regenerated active form of acetylcholinesterase and the phosphorylated 2-PAM. An important notice is that phosphorylated cholinesterases may undergo a dealkylation reaction of the organophosphorus moiety, leading to an aged enzyme, and this is the process called aging. This process leads to anionic phosphate groups, which are much less electrophilic and therefore much less likely to undergo hydrolysis by an antidote. This is why antidotes are recommended to be given as soon as possible in order to avoid cholinergic toxicity and therefore death. Thank you guys for watching, and if you have any questions, please do not hesitate to leave them in the comments section below. Don't forget to leave us a thumbs up and subscribe to Parasympathomimetic Academy YouTube channel for more and more videos.